All right, so I hope I'm audible, loud and clear. So the topic of discussion for this evening is mathematics of control theory, and the subtopic that we are going to talk about in this session is going to be differential equations, transfer functions, and state space, all of which are integral parts of control theory, and we'll try and see the mathematics behind it. Okay, so. Right. So usually the undergraduate point of view of control theory is of this type, where we have so-called a block diagram. So we see a system, a dynamical system, as a signal processor. So often we call this as a plant, right? Where we have an input, as Harish was saying in the first session, which is input and output, and there is some law that describes the behavior of this system, right? The behavior of the system is given by some law of some law which tells us which u input and output, which yu functions are going to be in the behavior of this plant, right? There are many other ways of describing such systems also, namely signal flow graph, right, or an input-output map. But all of this are a way, it's just like a different way of saying the same thing, right? And perhaps the most, what should I say? Perhaps the most widely used such description of a dynamical system is via what is known as a transfer function, which happens to be the ratio of the output Laplace transform to the input Laplace transform under the assumption that there are no non-zero initial conditions, right? Yeah. Okay. Now, in this scenario, what we are assuming, however, is that this is a single input, single output system, that the number of inputs is just one, the number of output is also just one, right? So if there are multiple inputs and multiple outputs, like for example, if ut at every point of time is m valued, and suppose yt at every point of time is p valued, then this transfer function gs will no longer be a transfer function, but however, rather it's going to be a matrix of the type that has p number of rows and m number of columns, where the entries are all rational functions in the Laplace variable s. Okay. Now, to handle such thing is really difficult. We are having, as we'll see very soon in this course, that when we have, matrices of course are like much more difficult to handle than just numbers, right? Yeah. Now here we have a matrix whose entries are not just numbers, but entries are ratios of polynomials in S, right? So that's why for a multi-input, multi-output system, although it's not impossible to describe such a system using transfer functions, but it really is not perhaps the best way to do the description, right? So therefore, for MIMO systems, multi-input, multi-output systems, transfer functions doesn't seem to be the natural choice, right? Now, secondly, and perhaps more importantly, transfer functions always assume that the initial conditions are all zero. Yeah, if you remember from our undergraduate control course, that when we are obtaining this Laplace transform, such a Laplace transform, will, when you take Laplace transform in general, then the trick is, the theorem that we use the most for this is that when we are taking the kth derivative of a function and we are looking at the Laplace transform of that, then that happens to be s to the power k Laplace transform of the function f. But this is true provided initial conditions are all zero. Otherwise, there will be whole other terms that will appear with the initial conditions. Will appear of the initial conditions. So therefore, the initial conditions being 0 is a necessary assumption for us to have the transfer function of such a dynamical system, which is actually described by differential equations, right? So that's an assumption which is not very reasonable to make. Yeah. So 0 initial condition is not a reasonable assumption to make. Then further, if our system happens to be, say, time varying or suppose nonlinear, then this transfer function idea completely breaks down. Yeah, there is no way whatsoever by which we can represent the system by a transfer function when there is either nonlinearity and or time variance in the system. Okay. However, there is another way of representing such dynamical systems, which actually is much more general, yeah, and also more fundamental, right? And that happens to be differential equations. Okay, and this is not a new way of looking at systems. This has been there. Dynamical systems were being described as differential equations, and in fact, first order differential equations. So no matter, so as we'll see very soon, no matter what is the model, the ab initio, first principle model may give us a higher order differential equation, but we can always convert that into a first order differential equation, which we call the state variables. And that happens to be a description of a system which is much more general. It was being done as early as 19th century, mid to end 19th century. Yeah. However, it sort of lost its appeal in the 1920s and 30s when a lot of classical frequency domain techniques were being developed for control systems. However, in the 1960s, mainly due to the efforts of Rudolf Kalman, the idea of state space, first order differential equations, state variables, yeah, that idea was popularized. And then from then onwards, modern control theory has depended heavily on the state space description or first order description of dynamical systems. And that is what we are going to study in this lecture. Okay, now, what do we mean by such differential equations? In the first session, we have already seen such differential equations. What we have for a differential equation what we call a differential equation is something like this. So first, we'll keep things easier and we'll consider once again seesaw systems. So seesaw means single input, single output. So a differential equation for a dynamical system with single input, single output is going to look something like this. So remember, y is our variable of that y is the symbol that we use to denote output, and u is the symbol that we use to denote input. And a differential equation is going to look something like this: dny dtn plus an minus 1 dn minus 1y dtn minus 1 plus plus a1 dy dt plus a naught y is equal to some br dru dtr plus br minus 1 dr minus 1 u dt r minus 1 plus plus b1 and du dt plus b0 into u. Right, so this is the description of a seesaw system, seesaw dynamical system given in the differential equation form. Right, but what do we get from how do we solve such a differential equation? You see, for control theory, the first thing that we need to understand is this is the equation that is given to us, which we get by doing some first principle modeling of the system, right? So we put various laws, as Harish was saying in the first session. We get some natural laws, yeah. Physics gives us those natural laws. We apply those natural laws to that system, and that gives us this dynamical system, yeah, in terms of a differential equation. But remember that this differential equation does not immediately give us the behavior of the system, because we don't know from this differential equation as to if I excite the system with this kind of an input. Suppose this is my input, yeah, what is the output that we expect? Yeah, the answer lies in solving this differential equation. But the question is, how do we solve such a differential equation? We have seen using Laplace transform and transfer function idea that if there is zero initial condition, then we do this Laplace transform, inverse Laplace transform and things like that to get the solution. But what we are going to see here is a much more fundamental way of solving differential equations, and in the process we'll realize how important or how how essential it is to write these equations in the state variable form in the so-called state space. Okay, now the idea of state space is actually kind of very simple, yeah, and in a way it is kind of borrowed from physics, yeah. However, the physicists call these variables as phase variable as opposed to state variables. Okay. Yeah, and I'm sure all of us have already seen such phase variable formulation of differential equations. You know, uh, Newton's laws. Yeah, Newton's laws. The second one tells us that if we have a mass which is moving, right, then the force. Okay, let me use small font. Yeah, the force Ft is equal to m, the mass of the body, times the acceleration. So if I use x as my displacement variable, then this is okay. This is the differential equation, right? So this is one example where the natural law, namely Newton's law, Newton's second law, Newton's second law of motion, tells us that a system where there is this mass and this mass is being, moved by a force Ft, and its position is x. Yeah, then x, the variable, this variable satisfies this differential equation, and it's a second order differential equation, right? And one can convert this into a first order differential equation by defining this, that okay, x is my displacement, fine, but I define a variable called velocity, or if you want you can define it as a momentum. This velocity v happens to be x dot, right, which also is same as defining p to be equal to mx dot, the momentum, right? And then we have this equation, sorry, then we have, from here we can have this equation that p dot, rate of change of momentum, is in fact equal to the force. Combining together, what we have is these two equations. First we have x dot equal to 1 by m into p, and p dot is equal to f, right? Yeah, is that all right? We can just write this equation in these two equations together in this form. These two equations we can combine and write like x p and its derivative is then equal to, this is before, is then equal to 0, 1 upon m 0 0 xp plus 0 1 into ft. Yeah, so this is the phase variable description of the system, right? So the general form of this phase variable description happens to be uh, the general form of this phase variable description happens to be that in general, if it's a system with n particles instead of just one single particle, then each of those n particles will have a position variable and a momentum variable, right? So we'll have n such position variables, which is 3n, because in 3D space there will be 3n variables, and momentum also in 3D space can be a 3D vector. So therefore there will be 3n such momentum variables, to total 6n number of variables. They together will give us the phase variable x and p, yeah, the vector x and the vector p, and its derivative is going to be equal to, in general, some function, some function of this 6n tuple, sorry, 6n tuple of position and momentum, yeah, and also some forcing function, which let's say we are calling for the time being as ut. So this is the phase variable description from physics, right? What this is pictorially often presented as, this is like, say, some space where we have, some way of depicting, although it's going to be impossible to depict this here, because this has, even for a single particle there are 6 variables, right? So it's going to be 6-dimensional space where everything is happening, which is impossible to describe here, impossible to pictorially represent here, right? So we have this xp space, the phase space, and every point here is the phase of the system at some particular time instant, right? And this equation actually tells us that what is the rate of change of this system as far as the phase is concerned. That means at some time, let's say this is the phase, then at this point, what would be the phase in the next instant? That is the rate of change, yeah, and that is given by this equation, which is this one, which is often denoted as some arrows. This arrow tells us that how is at this point, what is the rate of change of the phase. And in physics, often this is called a vector field. All right. What we are going to see is that this idea of this, vector field, how this helps us in describing the control, the system that we are talking about. Yeah, where we have a differential equation, which, as I said before, looked like this. So remember, this is the differential equation that we are interested in, and we want to use this, an idea similar to this phase variable, to describe our situation here. All right. So I hope this is clear. So okay. So is this clear? So while the results of the poll is awaited, maybe if you have any questions, we can take those questions, and before we move ahead.
Sir, in the previous session, there was a notation used. I just wanted a clarification.
Sure.
In the
May I know who am I talking to?
this is Dr. Rajat.
Hi, Dr. Rajat. Good evening. Yes.
Yeah.
Yeah, please go ahead. Yeah.
So, in the previous session, when the dynamical system was introduced as a tuple of three,
Hmm.
T, W, and B, B
Hmm.
was given as a subset of W power T.
Right. Yeah.
Yeah. So W
W
power
power.
T did not exactly follow what that notation meant.
I see. I will tell you what this is. Okay. Hmm. Let me get back to my workspace. Well, let me delete this. Yeah. Right. So the notation actually is kind of a fancy way of describing something really simple. I will tell you. So suppose I have a set A and another set B. These two are two sets, any two sets, just sets. The notation A raised to the power B, this is by definition the set of all maps phi from the set B to the set A. Yeah, that's it. One may ask that why this power notation, because you see, if you have uh, right, so if you have say B, which is just let's say binary, yeah, say 0 comma 1, right, suppose this is B, then indeed if you look at all possible maps from 0 comma 1 to any arbitrary set A, then the total number of possible maps is actually A squared. In the sense that if once again A is also a finite set, then the total number of sets, a total number of such maps will be the cardinality of A raised to the power of 2. Yeah, because you have a number of choices, and whatever number of elements is there in A, you have that many choices to choices for sending 0 to by a map, and similarly these many choices for sending that number 1 to. Right. So therefore, the total number of maps is A raised to the power. Okay, sorry, my bad. A to the power B. Right. And to this, so borrowing from this idea with finite sets, this symbol I think has been invented to describe this set. But even if you don't don't buy all these things, just remember that this means that this is all possible sets. This weird symbol is just used to denote all possible maps from the set B to the set A. So therefore, when we are talking about indexing set T and signal space W, when I write W to the power T, this actually denotes all possible maps from the set from the set T to the set W. Yeah, and you can easily see that this actually makes sense. Suppose I have a like the circuit example where we have RC circuit. Yeah, there is this V and there is this current I. Okay. Now, if I look at this VI, this VI guy, this actually is a function of time, right? So that way I can view this as a map from R to R2. Yeah, indeed, this is a map like this because it takes a time t and tells me what is the value of the voltage at this time t and what is the value of the current at this time t. So it's a two tuple, it's an element from R2. So therefore, Vi is indeed a function from R to R2. In other words, Vi in that case is indeed an element in, okay, in this notation it will be R2 raised to the power R. This being W and this being the set T. Yeah. And because we call these things as trajectories, yeah. So every trajectory is from this set when we are looking at the behavior, which happens to be the collection of trajectories that are allowed by the natural laws. Obviously, then the behavior is going to be a subset of W raised to the power T. Yeah, because it's a subcollection. Okay, yeah, trajectory here, by trajectory we essentially mean elements from the behavior. Yeah, any typical element from the behavior will be called a trajectory. This is a general definition which doesn't involve things like whether it's a system evolving over time, whether it's a system evolving over space. We don't go into that. Then we say that any element from the behavior is a trajectory. Yeah, we mean such a map. Yes. May I know who I am speaking to? Yeah. Right. So, Dr. Rajat, was this clear?
Yes, very much. Thank you so much. Thank you.
Yeah. Thank you. No problem. No problem. Right. So, I really appreciate such questions. Right. So, only yeah. So now we were saying that our goal is to obtain such a phase variable kind representation. Yeah, where the representation can be described by such a vector field of showing us the rate of change only of the phase. Yeah, for a general differential equation is what we want. But we will do this in two steps. Yeah, we'll call it case 1 and case 2. Case 1 happens to be this one. For case 1, we consider the differential equation which looks like this. We are saying that no differentiation on the input, right? Which means we have an equation which looks like this: dn y dtn plus an minus 1 dn minus 1 y dtn minus 1 plus dot 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 up to a1 dy dt plus a naught y. This is equal to just u. Yeah, that's what we mean when we say that there is no differentiation of the input. Yeah, is that all right? Okay, now how do we do this? Once again, exactly same idea as before for the phase variable. Yeah, all we have to do is the following. So we define. What do we define? Okay, we define x1 to be equal to y, right? Then we define x2 to be equal to x1 dot, or which is also equal to y dot from our earlier definition. Then we define x2 as, sorry, x2 we have already defined, x3 as x2 dot, which is the same as x1 double dot, which is the same as y double dot. And I'm sure you understand what's going on. We go like this, and finally we define the nth variable xn to be equal to, well, I have not been very cautious while writing this, so I have run out of space, so please forgive me. I will correct myself. Yeah. Oops, sorry. I define the final one, xn to be equal to xn minus dot. Oh, by the way, by this dot I mean for one's derivative. So it's actually required to define. So for any variable, y dot is by definition dy. I think I have read somewhere, I'm not very sure though. I think this dot notation is something that was used by Newton, whereas this dt notation is something that was used by Newton's arch rival Leibniz. Yeah, Newton actually didn't even call them derivatives; he used to call them fluxions. For we sort of credit Newton with the discovery of differential calculus, right? But Newton didn't even call it derivative or differentiation. He used to call it fluxions. Yeah, this was the spelling. Right. So this dot is just derivative. 2 dot means 2 derivatives and things like that. So this xn is x minus 1's derivative, and this must be x minus 2's double derivative. And if we keep doing this all along, what we get is that this must be nothing but x n minus 1 n minus 1's what should I write? It's uh, it's n minus first. Oh, sorry, my bad. Just being too sloppy. Let me write it properly. dn minus 1 dtn minus 1 of x1, right? And x1 is y, so it is the n minus first derivative of y. This is just the way, just one step after the other we define it like this. Now one may say that, okay, what's the benefit of this? Yeah, well, the benefit happens to be the following. We see that if I look at this collection now, x1 up to xn, I say this is my state variable, x. Yeah, and this is actually behaves like the phase variable. That means the whole dynamics of the system actually is encompassed by a first order differential equation in this variable x, that is in this vector variable x, x1 up to xn. Yeah, now in what sense, right? So let us see what's going to happen with this guy. So I claim that with this guy, with this x, ultimately we'll be able to write this as x dot, that is one's derivative of x dot, that is equal to dx dt, is going to be some matrix A into x plus b into u. Yeah, like this, where b is a vector. This is the claim. The question is, how do we prove this claim? Okay, in fact, it's very simple, absolutely simple. Let's see what it involves. Is just looking at how dx dt is just look at the definition of x, then from there try and infer what's going to happen to the derivatives of all these variables. By that, construct the matrix A and construct the vector B. That's it. So all it boils down to is to find out, to describe this matrix A and the vector B. So first we're going to yeah. So we'll just do it step by step. Yeah. Get all the entries of the matrix A and the vector B step by step. That's all that we're going to do now. Right? Okay. So first thing, x dot, what is the first entry in x dot? Of course, x1 dot. Now what is x1 dot? What is x1 dot? Well, x1 dot from our very definition itself is nothing but x2. That's how we have defined. What's going to happen to x2 dot, which is the second entry in x dot? That's by definition x3 dot, right? And we can continue all the way, but okay, I made a mistake. I put an extra dot here. x2 dot by definition is x3. Yeah, my bad. x3. And then we can go all the way up to how much? Remember, not so fast. We can go up to only xn minus 1 dot, which by definition is xn. But we cannot go any further because we have not, if you have paid attention to what I was doing in the last page, remember that I did not define xn dot. I mean, there was no definition while coming up with the definition of these variables that involved xn dot. Only up to xn we have defined, right? There was an extra definition. Yeah, I agree. x1 equals y. That was an extra definition, but this didn't involve any derivative, so it doesn't show up here on the left hand side. However, on the left hand side, this guy does show up, which we have not defined yet. But then, actually, we can come up. We can figure out what this xn dot must be from the basic differential equation that we were given, right? And this is how. So okay, remember what is xn? I said xn is xn is, so this is d dt of, remember that the bottom right corner where I just jotting down something which may not have been very understandable, but try and understand that this is what this guy was, that what I was trying to write. This is dn minus 1 dtn minus 1 of y actually. That was xn, and xn dot must be one more step of differentiation on that variable. If that is so, then this is nothing but dny dtn, right? And voila, because we already have an equation with dny dtn there. Okay, what was that equation? Okay, let me just rewrite that equation here. The equation that was given to us was dn dtn plus a naught, plus a n minus 1 dn minus 1 y dtn minus 1 plus dot 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 plus a 0 y was equal to u. Now in the light of these new definitions that we have done, this is nothing but, so let me write everything in terms of the new definition. This is nothing but xn dot plus a n minus 1, this is xn, right, by definition, plus a n minus 2 into xn minus 1 plus dot 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 up to a0 into x1, that must be equal to u, which then, so this is okay. Now this equation I could just write as, all these pluses I will remove, yeah, because I will take all these guys to the right hand side, when they become a minus. We'll get rid of this equal to sign as well. What I will do instead is I will write this is equal to minus of this, minus of this, minus of this, plus this, right? And then combined, you see what I'm going to get is the following. Combining all these equations, I'm going to get x1 x2 dot 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 xn. The derivative of this is equal to, well, this is the moment of truth that we have all been waiting for. 0 1 0 dot 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 all 0 0 0 1 0. This continues this trend, 0 0 0, and then we get a 1. Here we get a0 minus a1 minus a2 dot 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 minus an minus 1, multiplying x1 x2 x3 dot 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 up to xn plus 0 0 1 into u. Okay, this is what we have promised. This is my matrix A and this is my vector B. Yeah, is that all right? Now this is exactly like that phase variable description. Yeah, the way one does this is, the way one pictorially depicts this is, this is a general case. Before going to the general case, well, yeah, while doing the general case we can do that, or perhaps we can do it here also. Hang on, I think I can get rid of this definition now. Yeah, this I can get rid of. So if you remember what has happened here in this equation, well, the way to describe this is, suppose this is my output y, right, and which is defined as x1. Okay, and then suppose there is a block here such that this block is x1 dot, yeah, which we define as x2. Same variable x2 is defined as x1 dot. So what sort of a thing must this be? This must be an integrator. Yeah. Similarly, this x1 dot goes to another integrator block and gives us x1 double dot, which is the same as x2 dot, which is the same as x3. So like that. Yeah, ultimately we have the variable xn, which happens to be xn minus 1 dot. Okay. Now what does the equation tell us? The equation actually tells me that right, actually we need one more block. So let me just try and be a little pragmatic about my size of pictures. Right. Yeah, this is x3. This is x2 dot dot dot. Yeah, one more integrator block, which gives me xn minus 1 dot, which happens to be xn, and suppose there is one more such block which gives us xn dot, right? Now xn dot is equal to the input plus, with minus signs, various things like various blocks like this gets multiplied by a n minus 1. Yeah, this gets added here. X1 gets multiplied by A0. X2 gets multiplied by A1, the minus sign here. All this with the minus sign. Yeah, oh, sorry, I put an arrow wrongly here. Like this. And this guy also gets multiplied by the minus sign here, minus A2. And yeah, like this. Okay. So this becomes the way one represents this x dot equals ax plus bu kind of thing. So ultimately we do get something like x dot equals ax plus bu. Yeah, is that all right? Yeah. So pictorially, this. Yeah, Dr. Rajat. Yes.
How many inputs you are being assumed here?
We are assuming only one input. And we'll see what happens when there are multiple inputs. Initially I said that multiple inputs is like something that the transfer function approach is not the best way to handle. So I should sort of justify that state space is better as far as multiple input is concerned, and we'll see how. Yeah.
Sure.
In fact, I can tell you right away.
What should be the size of B? That's all.
Yeah, the B will be of proper size. If there are multiple inputs, then B should be of proper size. So if there are m inputs, if U is a vector in Rm for all time, then B must necessarily be a matrix of size n cross m. Okay, yeah, thank you, Dr. Rajat. Now, what is still sort of pending is that remember that this was a special case, right? When we did this x dot equals ax plus bu, it was a special case because it was a very special differential equation. Let me write down the differential equation here. Right. So this was the differential equation, which is not the general one, which is not this one. Yeah, not this. These derivatives didn't appear. Right, but then what do we do if we have those derivatives? It turns out that this is just the first step to get such a representation for for the general case as well. Okay, What we need to notice here is that we have missed, we actually need one more equation to describe the system fully, because our system didn't have x for its variable. X is something that I have created, if you remember. I was defining x1 equals this one, x2 equals this, x3 equals this, and so on. What my original variable was y, and of course u. U still appears here, but where is y? It so happens that I have to relate y uh, with this x. And how do we do that? Well, remember we have defined, no? We have defined x1 to be equal to y, which is a fancy way, a fancy way of writing this would be to write y equals 1 0 0 dot 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 1 0 into x, and we call this cx. So together the equation becomes x dot equals ax plus bu and y equals cx. And this is a form of equation that you have already seen in the first part of this of today's lecture. Is it all right? But still, we have not yet answered the question of what are we going to do when there are derivatives of the input. Okay. Now, it so happens that, you see, if we have the general situation, if we have the general case, then we have, say, a differential equation. So what we are going to do is, suppose this is my general differential equation, yeah, dny dtn plus dot 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 up to, I'm not writing all the way, yeah, because we have already seen them a couple of times. So I think we are already sort of conversant with this notation. D to the r dtru plus dot 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 up to b0u. Yeah. Now using these same coefficients a0 up to an minus 1, suppose we define this new equation, yeah, new auxiliary equation, which is not given to us. New auxiliary equation involving a new variable with a new variable. Yeah, and what is that? Well, dnz, new variable z, dtn plus dot 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 a0z equals u, like before, like an equation before. Yeah, I claim that, using these b's and this z, I can now write what y should be. Why is that so? Well, that actually takes us back to this Laplace transform idea. I mean, there are several ways by which one can show this, but perhaps Laplace transform will be the easiest one to show this. You see, look at this block. Yeah. So suppose I define this polynomial bs as br s to the power r plus dot 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 up to b0, and as to be equal to s to the power n plus dot 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 up to a1s plus a0. So in that case, the transfer function I have is bs divided by as, and this us gives me ys. Our transfer function idea tells us that from this differential equation, the corresponding transfer function happens to be this one. Yeah, but now, so let me repeat. What I have written is bs divided by as, us, and ys. But instead, now look at this one. 1 upon as, us gives us, let's say, zs, a new variable, and zs, when gets acted upon by bs, gives us ys. Yeah, this is just splitting of this like this, and then it automatically follows that y and Z must satisfy, in time domain must satisfy this property, that yt must be equal to br dr dtr into z plus br minus 1 dr minus 1 dtr minus 1 into z plus dot 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 plus b r b 0 into z, right? So see, various derivatives of z and the linear combination of that actually gives me y in that case. Okay, this is a trick that we can use to obtain a state space representation for the general case. How? Well, what we have done is, so let me get rid of this part. So consider this one. So with z variable, consider dnz dtn plus an minus 1 dn minus 1 z dtn minus 1 plus dot 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 plus a1 dz dt plus a0 into z is equal to u. But we've already seen that this means if we define x1 equals z, x2 equals z dot, x3 equals z double dot, and so on and so on, then d dt of x1 up to xn is equal to a, which is this matrix 0 1 0 is all 0 0 0 1 0 minus a naught minus a1 minus a2 dot dot minus an minus 1 into x plus 0 0 1 into u. Yeah, this is the representation. Yeah, but then what is y? Y is equal to, we have seen, br dr dtr z plus dot 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 up to b0 z. Now herein we have to make an assumption. What assumption? Suppose r is so we make this assumption that r is strictly less than n. If r is strictly less than n, then we can actually write y to be equal to br into the variable, see what is it, drz dtr. Yeah, and drz dtr is xr plus 1, right? And because I have assumed that r is strictly less than n, when I write xr plus 1, I am not going to exceed, this index is not going to exceed xn. It can at most be xn. Okay, so this is xr plus 1 plus this will be br minus 1 into xr plus dot 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 up to b0 into x1, which is a linear combination of the x variables. So of course this can be written as initially some zeros and then some br sorry, my bad, it's the other way around. So I start with b0 and then b1 dot dot dot, I go up to br, yeah, and then I have zeros, this into x1 dot dot up to xn, right? So then together, if I now define this as my matrix C, together indeed once again I have x dot equals ax plus bu and y is equal to cx, right, provided this is true. Yeah, this is a restrictive assumption, we agree. But we can relax this assumption partially though. We can actually make this r less than or equal to n. Yeah, how do we do this? Well, we just have to realize that, okay, in order for us to write this, I need r plus 1 to be less than n, less than or equal to n, which means r has to be strictly less than n. But then I can do the following also. I can get this D matrix in position, right? Instead of, so when r is equal to n, so then in that case, where should I write this? Yeah, for this general case, when I have say say n is r is equal to n, then I notice the following, that my differential equation actually transfer function wise actually is, so ys by us. So remember, when I'm saying transfer functions, I'm not, it may appear that I'm cheating, right? Because I wanted something better than transfer functions, but I'm using transfer functions to to prove my result. That's not exactly cheating, because I'm just using transfer functions as a placeholder for these differential equations. Yeah, if you look at this carefully, never have I ever in this case have used anything beyond differential equations. Although to make our life easier, to understand things in an easier manner, I am writing this differential equation using this placeholder f. That's it. Yeah. Now in this situation, if r and n are equal, that means the degree of this polynomial and the degree of this polynomial. Yeah, these were the polynomials, right? Bs by as. So if these degrees are the same, then in fact this can be written as some constant k plus a b tilde s and as, where this now degree of b tilde s is strictly less than degree of as, which happens to be n. So then for this part, I can write the state space representation, but this will not be my output. Yeah, output will be actual output. So I have to have a tilde kind of an output. Yeah, so I will consider this as my transfer function and obtain a state space representation, which will give me x dot equal to ax plus bu, but y tilde equals some cx. And then I will realize that this actual y is nothing but k times u plus y tilde. And so in this case, this will turn out to be cx plus ku. So this k in control theory is what is known as the D matrix, right? So finally, what we get? Finally, what we get is this one, that for the general case, we have x dot equals ax plus bu and y equals cx plus du. Yeah, and as Dr. Rajat was asking, in this particular situation, what we have done is for single input, which means b is a vector. So b is Rn, and C also is a vector because single output. So C is an element in R1 cross N, and D, of course, in this case is just a real number. But this description is so general that we can invoke situations where we have multiple inputs and multiple outputs. All that will happen in that case, that we'll have the same equation, x dot equals ax plus bu and y equals cx plus du, but here the matrices will be a n cross n, b will be n cross m, where n number of inputs, c will be p cross n, and d of course will be n, sorry, my bad, p cross m. These will be the sizes. Yeah, but this description will still be valid. Okay, I hope this is clear. Now at this point, I will give you a food for thought, something that you can think, before you join the next lecture. What would happen if the assumption that we made that r is less or equal to n, if that is not true, if that doesn't hold, what do we do then? Yeah, this is a food for thought for you. I am trying to write a, draw a bulb here. Let me write it properly. Doesn't look very good. Let me draw it properly. This is a food for thought. What happens when R is, this is not true? This assumption that we have made, what if this is not true? What happens then? Yeah, I will not give you the answer right away. Let me give that answer when we meet next time. But before that, I want you to sort of put some thought into this question. Okay. So I hope what I've done so far is clear. If not, please ask questions. Yeah, as I said before, that if you think that we are going a bit slow and this is something that you already know already, then you should let me know so that we can, sort of do a course correction to the lecture. Okay.
So, sir, a similar
Yeah.
formulation for different equations?
I'm sorry, Dr. Rajat, your initial voice was breaking, so I was not able to understand you. Can you please repeat your question?
No, I was just asking, do we have similar
Yeah.
formulations even for difference equations?
Yes, absolutely. For difference equations also, we have exactly the same way of doing this. Only thing is that the way we are defining the state variables here by taking derivatives, they will take shifts. So like if I have a, yeah, if I have, so my first state variable x1 is defined to be y, then x2 will be defined to be yn minus 1, or sorry, yn plus 1. Or was it k? Yeah, I think we were using k as the variable, as the index variable. Yeah, so x2 will be yk plus 1, shifted version of y by 1. Then x3 will be defined as yk plus 2, twice shifted version of y, like that. And we'll end up with this, with exactly same kind of an equation. Yeah, that also you can take as a food for thought. Yeah, then what happens when we have a discrete system? Okay. All right. Now, all said and done, we have this nice, first order representation. But how does this really help the, help the proceedings? How does it help us in any way going closer to the, to solving the differential equations? Well, it turns out that the solution is in fact pretty simple. Yeah, kind of very intuitive also. Suppose we have x dot, oh sorry, x dot is equal to ax plus bu. See, all the calculation involves solving this equation only. That cx plus du, which is y, there is nothing there. It's just a linear combination of x and u. There is no derivative, nothing. So it's not a differential equation. So there is nothing to be solved there. Only solution should take place here. Yeah. Now the question is, how do we solve this? From here we actually see something like this. You see, suppose xt is a solution of this differential equation, which means this indeed satisfies x dot t is equal to ax plus bu. Yeah, is it alright? Suppose I have another, say, xht, another sum function which satisfies xht dot is equal to a xht, just this much. Then what happens to this situation is that now if I look at xt plus xht, as Harish was saying in the first half, that functions can also be summed up pointwise. It turns out that this set of solutions for this is actually a kind of close under addition when we are doing additions like this. What do I mean by this is, look at the derivative of this guy now. Yeah, this derivative will be x dot plus xh dot. Now what is x dot? X dot satisfies ax plus bu, and xh dot satisfies axh, which is the same as a into x plus xh plus bu. Right? So that means if x is a solution and xh is a solution of this special equation, then x plus xh is also a solution of this equation. Yet this is something that is known as the property of the homogeneous part of a solution. This is like property of linear maps. So whenever we are solving for linear equations, right? A linear equation, you pick any solution and then choose things from the null space of that linear operator, right? Elements from the null space you can easily add to solutions and still produce new and new more solutions. So exactly same thing is happening here. There is some operator which I am not describing here, whose null space contains solutions of these equations, the so-called homogeneous equations. Right. So all one needs to do, and also one can show that every solution in that system can be obtained by looking at one particular solution and then adding all possible homogeneous solutions. Yeah. So what I'm trying to say here is that if x is a solution, then x plus xh is also a solution. This is the first part of the statement, and the second part of the statement is that every solution. So let me do this. So do something, and let me call it xp. Yeah, this is one fixed solution. Yeah. Now, oops, sorry, xp. Let x be any other solution, then there exists xh tilde satisfying the homogeneous equation such that x is equal to xp plus xh tilde. Yeah, this in fact is kind of very easy to show. You see, because I'm saying x is a solution, any arbitrary solution, and xp one fixed solution of x dot equal to x plus bu, then you see x dot satisfies ax plus bu, and xp dot satisfies axp plus bu. This then tells us that x minus xp whole dot must satisfy ax minus xp, which means x minus xp must be a solution to the homogeneous equation. You see, this is the homogeneous equation. Yeah, and this, all of you who have done a little bit of linear algebra would kind of immediately recognize that this is nothing but this situation when we are solving for ax equal to b, where a is some matrix, need not necessarily be square. When you're solving ax equal to b, the solution set in the x space is always going to look something like this, yeah, where the null space of a is this space. This space is a so-called null space of a, or kernel of a. And so if this is the solution set, this is the solution set, then this solution set can be written as, take any particular solution, take any particular solution here, and to this solution add stuff from here, from the kernel space, and that will give you the whole solution set. So the whole of solution set of this guy is actually given by a particular solution. Any particular solution, doesn't matter. This could be this one, could be this one, anything, any particular solution, but one fixed particular solution you choose. You call it x, call it xp. Then this set is given by xp plus null space of a. This is the solution set, and this is precisely what we are doing for this differential equation also. Obtain one particular solution and characterize the homogeneous part of the solution. That gives you all the solutions. So all we have to do is we have to characterize the homogeneous part of the solution. Remember, I need only one particular solution, but I have to characterize all possible homogeneous solutions in order to get all possible solutions of the system. Okay. All right. So how do I get the homogeneous part of the solution? What is the homogeneous part? Homogeneous equation is x dot equals just ax. Yeah. Now we solve this. We'll always be tempted to do the following. If it's just a single scalar variable, x dot equals ax. How do we solve this? This is nothing but dx equals a dt. Integrating, we get sorry, dx by x. If we integrate this from x0 to xt, this integral from 0 to t, what we get is, this is ln x minus, this is ln x minus ln x naught is equal to at, which tells me that this is nothing but ln x by x naught equals at, which tells me that xt is nothing but x0 e to the power at. That's the solution. Okay. It is very tempting to write this equal to xt is equal to e to the power at into x0. And I think all of you may have seen this before, this matrix exponential idea, that this is the solution. Okay. What I'm going to do is I'm just going to give you one very interesting bit of theory. I'm not going to prove it though. One very interesting bit of theory which actually kind of proves that this xt must be equal to e to the power at into x0. Yeah, let me try and do this quickly. I have 7 more minutes to spend. So this technique is known as Picard's iteration formula. I will not have time to actually go through it fully. I'll just mention it. Then perhaps we'll complete this in the next session that we meet. Okay. Picard's iteration formula or iteration scheme. So what is the differential equation that we have to solve? Dx dt is equal to ax. What Picard says is the following. In fact, Picard's iteration formula works for nonlinear equations also. What it says is the following, that keep on doing guesses, better and better guesses for x, the solution. Yeah. In what way? That okay, we are going to learn this solution by making better and better guesses. How is this learning done? Well, you see, why am I calling this learning? Because this is exactly like this we sort of like to think that machine learning is some new thing that that's emerging, becoming really popular, really important field of study. But this idea of learning is not something new, because iteration formula is just a similar kind of learning. So what is this learning? It says that, okay, instead of solving dx dt equals x, what is the difficulty here? Is because this x variable appears here as well as here, right? How do I solve for something that requires itself for solving? Okay, we can't do that. So therefore, make life easier and solve for this instead. Okay, make the k plus first guess of the solution x d dt that satisfies a x with the kth guess. Now the two variables are different. Yeah, and if I start guessing properly and then I sort of solve this, then I'm actually learning the solution, and in the limit I will have the exact solution, right? So what could be my best possible guess? Well, there is initial condition, right? I know that x at 0 is given to me, and that is x0. Let's say this is some real number, some n-tuple vector that is given to me. What could be my best possible guess? That it remains x0 for all time. So then my first guess x1, my first betterment of the guess x1 must satisfy this a into x0. This is my initial guess, yeah, which tells me what? Which tells me that x1, yeah, must be equal to, well, if you do this integration business, you will pick up 1 x0 again because the initial condition is required, plus now this will be a x0 integral 0 to t dt. But remember, this was a fixed one, right? So this is going to be x0 plus a t into x0, right? No, this is not the particular solution. I'm still on the homogeneous part. Yeah. So what will be the next guess? So what was my first correction? First correction was x1t, then will come out to be x0 plus at into x0. So then now how do I learn better? I mean, how do I learn and make my solution better? dt of x2t. Now the second guess will be a x1t, which happens to be ax0 plus atx0. And now if I integrate, once again I'm going to get x2t will be equal to the integration of this plus the initial condition x0, plus this will give me again at into x0, and this guy here will give me at squared by 2 factorial into x0. You see now what is going on? You're going to approximate the e to the power atx0 as you move along, doing better and better guesses of the solution by learning the solution using this learning formula. This learning formula is known as Picard's iteration formula.
So the coefficient of t square, should it not be a square?
Right, and this would be a square, right? Yeah, right. Because there is a also, right? Let me see, why did I make a mistake? Yeah, this is a square. Right. Thank you, Dr. Rajat. Yeah, my bad. Yeah, otherwise we don't even get the formula for e to the power at. So in the limit, so x nt, the nth guess would be x0 plus at x0 plus a squared t squared by 2 factorial into x0 plus dot 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 up to a n t to the n factorial x0. And in the limit, the best infinity will in fact be xt, which is given by this e to the power at into x0, which is identity plus at plus dot 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 up to a to the n t to the n factorial dot 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 into x0. This is the solution, right? We have run out of time. We're just in time. I am not going to talk about the particular solution today. Maybe we'll talk about it the next time we meet. And also, next time we'll see how do we calculate this matrix exponential. What is the physical meaning of the state variable that we have created? In fact, it is called the memory of the system, right? And then we'll see that how change of coordinates actually helps us in uh, getting not only the matrix exponential much more in a much easier manner, but also lets us do all sorts of things like as we'll see later on, perhaps that how pole placement, controllability, all these things, how this canonical forms really help us, and how canonical forms actually are a manifestation of change of coordinates. Right. So with this, we put an end to this session. I'll be happy to take questions.